For 20 years, there has been one golden rule in computing. If something is too slow, throw more silicon at it. More cores, more memory, more racks, more power plants humming in the desert. That rule built the entire AI industry we see today. But what if the rule was wrong? What if the fastest way to speed up AI has nothing to do with adding more chips at all? Researchers in China just tested that idea. And the number they came back with is almost too strange to believe. Not double the speed, not 10 times the speed, 149 times the speed. And they didn't do it with a bigger processor. They did it with beams of light. This video takes real work to put together. So if it's useful to you, drop a like and subscribe so you don't miss the next one. Now let's get into how a handful of small chips beat a full-size GPU almost from a standing start. Every AI chip on the market today is a math monster. It can chew through trillions of calculations every single second. But math is only half the job. Before any chip can multiply a single number, it has to fetch that number from somewhere else. That somewhere else is the problem. Data has to travel from memory to processor, from processor to processor, sometimes from one server rack to another, clear across the room. Every trip costs time. Every trip costs power. And a chip that's waiting on data isn't doing math, it's just sitting there, burning electricity for nothing. Engineers gave this problem a name years ago: the memory wall. It's arguably the single biggest bottleneck holding modern AI back. The usual fix is to stack memory closer to the processor, shrink the distance between components, and build denser, faster copper connections. That approach works up to a point, but copper has limits. Push electricity through a wire fast enough, and it starts fighting you back. It radiates heat. It degrades over distance. It needs constant correction just to keep the signal clean. And when a task gets split across many chips, the problem multiplies. One chip finishes its job and then just waits. And waits for the next chip to catch up. Add more chips to a setup like that, and on paper your total power goes up. In reality, you're paying for horsepower that spends most of its life idling. Picture an assembly line building a toy in 5 separate steps. If one single worker does every step alone, start to finish, nothing else can begin until that first toy is completely done. Hire 4 more workers and put them on the same lonely task. And you've gained nothing, they're all still waiting on the same toy. Now, change the setup. Worker 1 finishes step 1 and immediately hands it off. Then start step 1 on the next toy, while worker 2 begins step 2 on the first toy. Within just a few cycles, every worker is busy at once, each handling a different stage of a different toy. Finished products begin rolling off the far end, continuously, no pauses, no waiting. That is exactly the trick a team at Peking University pulled off, except instead of factory workers, they used chips. And instead of a conveyor belt, they used light. The setup had 3 core pieces. First, 5 FPGAs, reconfigurable chips that can be custom wired for one specific job instead of running general-purpose code. The team assigned each FPGA exactly 1 layer of a 5-layer AI model, so each chip only ever had to do one thing over and over extremely well. Second, every chip got its own optical transceiver, a small device that converts the chip's electrical signal into light, fires it across the network, and converts incoming light back into electricity on the other end. Each of these ran at 400 gigabits per second, an enormous amount of bandwidth for a single link. Third, tying it all together was a 6x6 photonic switch, built on a glass substrate, capable of routing any input to any output without one signal interfering with another. In testing, it moved data at 400 gigabits per second with 0 errors and no need for signal boosting along the way. Why does light beat copper here? Because photons don't fight each other the way electrons in a wire do. Different wavelengths of light can travel through the same glass path simultaneously without interference, and they lose almost no energy over distance compared to a fast electrical signal. Most importantly, an optical switch doesn't need to inspect, queue, and forward each packet the way a conventional network switch does. It's simply a clear path for light to travel through, which strips out an enormous amount of delay. The system wasn't fully optical. To be clear, the FPGAs still crunched numbers electrically. Memory was still electrical. Only the connections between chips ran on light. It's a hybrid: light for the talking, electricity for the thinking, and that hybrid approach is exactly why it's practical rather than purely experimental. The team tested the setup on a 5-layer model, trained to clean noise out of small black and white clothing images, 3 2x3 2 pixels each, a dataset called Fashion MNIST. They ran 1,000 images through the pipeline in batches of 10. Total time on the light-linked FPGA system, about 105 microseconds. That's roughly 1/10 of a millisecond for the whole batch. The 5 FPGAs combined were only capable of about 1.97 teraflops of peak performance, a fraction of what a modern GPU can theoretically deliver. Then they ran the identical job on a standard GPU, boasting nearly 17 teraflops of peak power, more than 8 times the raw compute of the FPGA cluster. The GPU took 15.6 milliseconds to finish the same batch. Do the math, and the light-linked system came out about 149 times faster, while burning roughly 1/9 of the power. The GPU wasn't lazy. It was simply stuck, constantly saving results, reloading rules for the next layer, and fetching data back out of ODITE. Memory between every single step. All that shuffling ate more time than the actual math did. The FPGA pipeline never stopped moving. Once it filled up, data streamed continuously from chip to chip through the optical switch, and nothing ever sat idle. Quick pause: if this kind of breakdown is useful to you, go ahead and subscribe now so the next one lands straight in your feed. Before anyone declares Nvidia obsolete, a reality check is in order. This test used one small 5-layer model on tiny images, already trained ahead of time. No training happened here, only inference. It compared 5 custom chips against a single GPU, not against the massive clusters that power real-world AI products today. The team also never published a full system-level power measurement. The 1/9 the power figure covers compute only, not the transceivers, switch, and support hardware running around it. And scaling this up to handle billion-parameter models would require vastly more channels, smarter scheduling, and software that doesn't yet fully exist. Flexibility is the real trade-off here. A GPU can run almost any model you throw at it. This pipeline was custom-built for exactly one job. Hand it something different, and performance could collapse. Here's the real takeaway. This isn't proof that light beats silicon everywhere. It's proof that times how you connect chips times can matter more than times how powerful each chip is, times at least, for tightly defined, latency-sensitive tasks. Self-driving systems, medical devices, and real-time inference tools all care more about instant answers than raw peak power. And that's exactly where a fixed optical pipeline could shine. For China specifically, facing restrictions on top-tier chip access, squeezing dramatically more usable performance out of modest hardware is a strategic win, not just a lab curiosity. Meanwhile, companies like Nvidia are pouring resources into their own optical interconnects. Because everyone in the industry already knows communication, not raw math, is becoming the next real bottleneck. The lesson from this experiment isn't that a faster chip is coming. It's that a smarter times system times might matter more than the chip inside it. If you found this breakdown useful, hit like and subscribe so you don't miss what's next, and check out the related video on the global chip race linked below. Do you think optical interconnects are the missing piece that unlocks the next leap in AI? Or is this result too small, too custom, to threaten GPU data centers as we know them? Drop your take in the comments.